Welcome to ECE 302. This is Lecture A.9 on cross-correlation through LTI systems. I'm Professor Stanley. In the previous lectures, we talked about a very interesting problem where you have a random process x of t going through a linear time invariant system with an impulse response h, and you get an output y of t. We looked at the autocorrelation function Rx, and then we also look at the autocorrelation function of Ry. Correspondingly, we look at the power spectral density of X, and then we also look at the power spectral density of Y. In today's lecture, we're going to learn about something also very, very relevant, which is the cross-correlation, which is the correlation between X and Y. Okay, here, if you recall, these are always the autocorrelation functions between Y and Y or X and X. How will the correlation be between X and Y? This is the focus of today's lecture. So if you try to have a overview of what we are going to do in this lecture, I'm drawing you a diagram. In this diagram, you can see that what I want to know is the correlation between x of t and then y of t. Now, this is really talking about the correlation between two random variables. One is x of t, the other one is y of t. And because my y is not an arbitrary y, this should give me some information about how this x is translated to give you the y. In addition, because I know that x and y, they are both y-sense stationary processes, what I should expect is that this correlation function should also be somewhat related to just the time difference between the two time stamps that I'm looking at. In particular, if I'm looking at x, not at t, but t plus tau, and then my y is looked at t, I can define this quantity. Similarly, I can also define the quantity of y of t plus tau and the x of t. These are more or less the same thing. I can look at this quantity, and we can also look at this quantity. Both quantities are telling us the correlation between one point in the input versus another point in the output. How are these correlated? These are different from the autocorrelation function, where the autocorrelation function you're looking at x and x. Autocorrelation function of y, you're looking at y and y. Here you're looking at the cross correlation between x and y. These two quantities will lead to the thing what I'm calling here, which is the Ryx and Rxy with this time gap at tau between the two. Okay, so today's lecture will be mainly focusing on the thing in the middle, which is the cross correlation function between the two processes as the x goes through the LTI system. To discuss the cross correlation, I really need to first define a concept called the jointly y-sense stationary processes, because in the previous diagram we know that x is y-sense stationary, y is y-sense stationary. We don't really know whether the product of x of t plus tau and yt, that kind of thing, will it maintain some kind of y-sense stationary processes, and therefore we need to define a notion called the jointly y-sense stationary process. What it means is that x is y-sense stationary, y is y-sense stationary. Furthermore, the cross correlation function, which is this is the cross correlation function between x and y, one at time t1, the other one at time t2, which is also defined as the expectation of x at t1 times y at t2. This is a function of t1 minus t2. Okay, now you can see that if x is y-sense stationary, you already have Rx of T1 and T2 equals to Rx of T1 minus T2. That is given by the autocorrelation function. Same for your Y. Having both does not automatically give you this Y-sine stationary property for the cross term. In order for the cross term to be also Y-sine stationary, you really need to assume, or you need to define it to be Y-sine stationary. And here is what we call the jointly Y-sine stationary. If your if your cross correlation function Rx and Y can be written as they are jointly Y-sine stationary, then Rxy, T1 and T2 can be written in terms of T1 minus T2, and where T1 minus T2 can be defined as this tau. Okay, so tau is really T1 minus T2. Well, in other words, you can say that my Rx of tau is defined as the expectation of x evaluated at t plus tau xy, okay, and then y evaluated at time t. This is my definition of the cross correlation for a pair of random processes x and y, x at t plus tau, y at tau, y at t. Okay, so now we have defined the jointly Y-sine stationary processes, and we have also defined what do I mean by the cross correlation function. I want to mention one very important property about this cross correlation function, which is that R of xy of tau is equal to R yx of minus tau. Now remember there's a minus here. This function is not symmetric. Okay, unlike Rx Rx of tau, this is equal to Rx minus tau. That is a symmetric function. But this Rx of xy of tau, as you flip the order of x and y, you need to remember putting a minus sign. The reason is the following. You can start by looking at Ryx at minus tau. This is defined as y and x. The time gap is minus tau, so you have t minus tau, and then you have t. This is the same as you just switch the order of this product. You have xt and y of t minus tau. Then, since this is Y-sine stationary, you can just shift them by a certain amount. Or in other words, you can just define a substitution of t prime equals to t minus tau, and therefore t will equal to t prime plus tau, and then t minus tau will equal to t prime. And since they are both jointly Y-sine stationary, you can just look at the time difference between these two timestamps. That will give you a tau. Okay, and therefore you have shown that R of yx equals to R of xy with a minus sign present in the argument. So I want to show you an example of how these can all be calculated. The example goes as the following. You have a Y-sine stationary process, x of t, and then there's another Y-sine stationary process, n of t. They're both Y-sine stationary. The expectation of x is mu x, the expectation of n is 0. So essentially you can treat this as a signal, and then here is your noise. So you have these two, then you compute this y is the sum of a signal and noise. You want to show that x and y, they are jointly Y-sine stationary. Okay, and we want to find this cross correlation function between x and y. Okay, so before we actually show that this x and y, they are jointly Y-sine stationary, we first need to verify that y is Y-sine stationary, because in order to prove that x and y, they're jointly Y-sine stationary, the first thing is to prove that they're both Y-sine stationary. So to show that y is Y-sine stationary, we can just look at the mean and also the autocorrelation function and show that the mean is a constant and then the autocorrelation function is a function of the time difference. So in this particular problem, we plug in the definition of y, which is x plus n, and since x is a y-side stationary process with a mean of mu x. The mu x will come out, and this n is a zero mean, so it will be gone, and therefore you can show that the mean of y is a constant. For the autocorrelation function of y, I am evaluating at two different timestamps, t1 and t2, and therefore I'm looking at y at t1, which is x at t1 plus n at t1, and then I have x at t2 plus n at t2. I multiply them, but since they're independent, and therefore many of these product terms will be gone, because if you look at this, expectation of x at t1, if you multiply with n at t2, that could be one possible cross term as you expand this quadratic equation. This is just the expectation of x at t1 times the expectation of n at t2, because these two processes are independent. Now this will give you a mean of mu x, and this will give you a mean of 0, and therefore all the cross terms between x and n, they are gone. What remains will be the self terms, which is x and x, and then n and n. If you look at these two, they will give you the autocorrelation function of t1 minus t2 and autocorrelation function of n. They can be written as t1 minus t2 because they are both y-side stationary processes. And therefore, you have shown what? You have shown that the autocorrelation function of y, which is a function of t1 minus t1 and t2, it is indeed a function of just t1 and t2, and as such, y of t is also y-side stationary. To show that x and y, they are jointly y-side stationary, we can check the cross-correlation function. The cross-correlation function is defined as expectation between x times y, where x is evaluated at t1, y is evaluated at t2. So what do we have? Well, we can expand this y of t2 equals to x at t2 plus n at t2, and then we can multiply them out. Then we will have expectation of x at t1 and x at t2, and then we have expectation of x at t1 and n at t2. So you have these two terms. The first term is just the autocorrelation function of x at t1 and t2. The second function here, this expectation, because x and n are independent, we can write them as the product of two individual expectations. The first term will stay, which is the autocorrelation function of t1 and t2. The other one, this is 0. Okay, it's a zero mean noise, and therefore this entire term will be gone. And therefore your cross-correlation function of x and y is, in this problem, is so interesting that it becomes the autocorrelation function. Okay, and so since the autocorrelation function of x is a function of t1 minus t2, it follows that the cross-correlation function is also a function of t1 minus t2. And consequently, you can argue that this x and y, they are y-side stationary. Now, the second part of this problem is to find the cross-correlation function between Rx and y. And then to do so, we know that the cross-correlation function, which is Rxy of tau, this is indeed just this Rx of the tau. Okay, the reason is that your Rxy of tau is this, right? Because your Rxy of t1 and t2 is the same as Rx of t1 and t2, and since Rx t1 and t2 is Rx of t1 minus t2, this is given by the problem. The problem says that x is y-side stationary, and therefore the autocorrelation function of x can be written as t1 minus t2. This is also written as Rxy of t1 minus t2. Okay, because Rxy, as we have just shown, it is jointly y-side stationary. And then you replace this guy by tau, and so you will have this the cross-correlation function being the autocorrelation function. And so as long as you can determine the form of the autocorrelation function of x, you will have the cross-correlation function for x and y. So this problem is solved. Now, as the random process x of t goes through the LTI system, we ask, is it possible to determine the cross-correlation function by looking at the impulse response? And the answer is yes. The cross-correlation function, yx, is defined as the convolution between h tau and rx of tau. And the reason is actually very simple. The ryx of tau, which is the thing that I have on the left-hand side, is just the expectation of y, t plus tau, and x of t. And then thus y of t plus tau can be written as this integration of x and t plus tau minus r and hr. And you integrate with respect to all the r's. Then the x of t will stay. Then you have this integration. The expectation can go inside this integration. Then you have the expectation of x of t and x of t plus tau minus r. And then don't forget there's also h. Okay, now if you look at this expectation here, this expectation is nothing but just the autocorrelation function evaluated at the time gap. The time gap is t minus r. And so you have this term here. And this is what? This is just a convolution between Rx and H. And therefore, you can show that the cross-correlation function between Y and X is the convolution between H and Rx. Now, to determine the cross-correlation function of X and Y, right? So here is Y and X. The correlation of x and y, you can just calculate this convolution and put a minus sign to this tau. Then you'll be able to get the other cross-correlation function. Given the cross-correlation function, we can further define the cross-power spectral density. The cross-power spectral density is the Fourier transform of the cross-correlation functions respectively for x and y and x. So these are all defined. And now, one thing that you may ask is, why is this cross-correlation function a convolution between x and Rx and H? Why don't we have this square term, or why don't we convolve it with another correlation, just like in the autocorrelation case? The reason is that when you look at this definition of Ryx, it is the expectation between y and x. There's only one h that is involved as you calculate the cross-correlation. This is very different from the autocorrelation function, where you have y and y, and each y you have an h, and therefore you have twice of the h, and therefore you have convolution followed by a correlation. In the cross-correlation function, you only have one y and one x. The x doesn't have any h. And so since you only have one h, you should expect to have a convolution between h and also the autocorrelation function Rx. So given the cross-power spectral density and also the cross-correlation functions, we also want to comment on this relationship between Sxy and Syx. It turns out that the Sxy is equal to the complex conjugate of Syx. It's just because of this symmetry issue that our xy of tau are equal to our yx of minus tau. This minus tau will give you this complex conjugate. Now, one more thing to notice is that the cross-power spectral density, if you want to relate it with the input power spectral density, it turns out that you need to put a complex conjugate on the xy, and there's no complex conjugate on yx. Okay, so it really depends on which direction that you go. Now, of course, if your h is real, both values will be the same. Okay, but if in general for any complex h, you need to put a conjugate on top of this x and y. Okay? And there's no conjugate for y and x. So let's look at an example. Let's assume that you have y sensation in the process x of t, and then you know is autocorrelation function. You also know the Fourier transform of the impulse response. I want to find the cross power spectral density, cross correlation function, autocorrelation function, and also the power spectral density of the y. So we want to find these four quantities. First of all, we can ask, given this autocorrelation function, what is the power spectral density? The power spectral density of this random process is just the Fourier transform of the autocorrelation function, where you can go to the table and find out the expression. And I'm giving you this expression here, which is root of 2 pi e minus j omega squared divided by 2. The Fourier transform of the impulse response is this, and therefore immediately we know that the cross power spectral density between x and y, that is defined as the complex conjugate of h times your input power spectral density. And since we have a term for this one, this is just itself because it's a real number. And then Sx is given by here, so you multiply the two, you'll be able to get this term. Now notice that there's a division by 2 here, and this 2 is gone when you multiply this h and also your s. So we found this one. Now what is the cross correlation function, Rxy? Then you just take the Fourier transform, take the inverse Fourier transform, you'll be able to get Rxy. So if you follow the table, you take the Fourier transform, you can show that Rxy is given by this quantity. Alright, so now what is the power spectral density of y, which is S of y? Now notice that S of y of omega is equal to magnitude square of h omega squared times Sx of omega. This is different from Sxy. Sxy is h omega conjugate times Sx of omega. So we have used this one, and now we want to look at this equation. So we plug in your h omega square, and then we multiply with s, we obtain this result. This is the power spectral density of y. And then you take the inverse Fourier transform, that will give you the autocorrelation function of y. In this case, it's given by this expression. So you can see that all these quantities can be readily computed as long as we know the system response, and we also know the input. Once we know these two, determining the output and also the cross terms, they are actually quite straightforward. Okay, so this is the end of today's lecture, and I hope you have learned some machineries to this random process problem. In particular, for today's lecture, we've gone through this cross correlation function and also the cross power spectral density ideas. The picture to remember is that you have this system, and then you have a random process x of t going in, you have random process yt coming out. Here you can get the Rx, and here you can get the Ry. But in some problems, we may want to find the cross relationship, which is Rxy and then Ryx. Both are pretty straightforward to determine if you know the Ry, Rx, and also here you need to know the h of t. Knowing all these will allow you to know the cross terms. And then the rest is just taking the Fourier transform. That will give you Sx, this will give you Sy, and then this will give you S of xy, and this will give you Syx. So now we have a complete picture of all the machineries to do random processes. And then we can have many applications of using these techniques, and that will be extremely useful. This is the end of this lecture, and I hope you have enjoyed this lecture. Now, in the homework problems, you will encounter some of these again. So I would encourage you to try the homework problems. Please also check out the past video for the homeworks. You go to the course website, you will see some homework videos. Try to watch those in case you have any difficulty of doing the homework. You're also very welcome to send an email to ask questions. I'll be very happy to help. Thank you very much.